All right, here's the second part of our weak acid, strong base titration. Now we have reached the equivalence point. The equivalence point is defined as number of moles of acid is equal to number of moles of base. That's what equivalence means. So in this case, we can see both the acid and the base 0.2 molar, both the acid and the base 50 milliliters. And so when we do the math, we get 100 milliliters or 0.1 liters. We have the same 0.010 moles of HNO2. Now we have 0.010 moles of OH minus. So now when we do this arithmetic, it comes out a little different. Now we've used up all of our acid. We've used up all of our base. We don't have anything left. All we have in the solution is 0.01 moles of NO2. So when we fill in our molarities, we have 0 moles of acid and 0.1 moles of NO2 minus, or molarity NO2 minus. But at this point, we're going to change from a Ka expression to a Kb expression. And the reason we do this is because now NO2 minus behaves as a weak base. We don't have a strong base anymore. It's all used up. The only base we have is NO2 minus. Can NO2 minus, remember the definition of a base is something that accepts a proton. Can NO2 minus accept a proton and become HNO2? Sure it can. So NO2 acts as a weak base. And we look at our weak base equilibrium reaction. We get NO2 minus plus water forms HNO2, as we just said, plus OH minus, okay? So now, when we look at this, we can write a Kb, or we can calculate a Kb, because remember, for a amphiprotic substance, or the conjugate substances, not amphiprotic, for conjugate substances, Ka times Kb is equal to the K of water. So that means Kb would then be equal to K of water divided by Ka. Well, that number comes out to be 2.5 times 10 to the minus 11th. Now, what does that equal? Well, if you look at the reaction that we've just written above that, it'd be the concentration of HNO2 times the concentration of OH minus divided by the concentration of NO2 minus. And since NO2 is acting as a base, there's going to be some dissociation going on. We don't know how much, so we write X. So I have X times X divided by 0.1. So X then becomes OH minus. X is equal to OH minus concentration. So that becomes 1.58 times 10 to the minus 6, because I plug in the values that I know, which in our case is NO2 minus, and I solve for the HNO2 value. And so I get 1.58 times 10 to the minus 6. But this is not H plus, it is OH minus. I can find the POH. It's just the negative logarithm of 1.58 times 10 to the minus 6. So that's 5.8. So that means pH is just 14 minus the POH, which would be 8.2. So suddenly, our pH has taken a very sharp jump up, order of 10,000 times less acidic, just by adding 5 more milliliters of base. Okay? Now, let's go to the next step, point F, which is now past the equivalence point. So again, I add 5 more milliliters of my 0.2 molar sodium hydroxide. Now, we've been down this road a number of times. We add up our volumes, 105 milliliters. We do our math to get the number of moles of HNO2, always been at 0.01. Now I have 0.011 moles of OH minus and 0 moles of NO2 minus. But now when I do my reaction, all of my acid has been consumed because it's the limiting reagent rather than the base. And that leaves me with 0.001 moles of OH minus and 0.01 moles of NO2. So OH minus is now 0.001 divided by 0.105 liters, and I get 0.00952. So we do have NO2 minus. We have 0.01 moles of it, and we just said it acts as a weak base. But the fact of the matter is, it's a weak base, and OH minus is a strong base. It's a much stronger base than the NO2 minus. So now we can pretty much ignore the effects of the NO2 minus because now I've got OH minus that's kind of greatly overshadowing the amount of NO2 minus. So we can ignore NO2 minus. It's not going to have an effect. All right, so now I do my POH calculation, which is just the negative logarithm of that 0.0952, and I get 2.02. That's POH. pH then is 14 minus POH, or 11.98. So I've taken another drastic jump up in the pH value as I get past the equivalence point. Now, let's take a look at what has happened. If we graph all 6 of these points, over here on the left, I've got my graph pH on the y-axis and the volume of sodium hydroxide added on the x-axis. And you can see, you sort of probably could surmise this when we started talking about how drastic the pH change is at the equivalence point. It's sort of linear. It's linear if you use a logarithmic, or in our case, we would call this semi-logarithmic because one of the axes is logarithmic and the other axis is linear. And so we call this a semi-logarithmic graph. But if we look at those first 4, A, B, C, and D, are almost in a straight line. Not quite, but pretty close. But it's not till we get till right before the equivalence point. Remember, the equivalence point was 50 milliliters. And you can see at 50 milliliters, the pH just goes up extremely quickly. So if you look at the difference between, say, 48 milliliters and 52 milliliters, the pH goes from 5 up to 11, or maybe even closer to 12. So 5 to 11 would be 6 pH units. That's a factor of 1,000,000. So the concentration of acid has decreased by a factor of 1,000,000 over the course of just a few milliliters. So now if we go back to the right here on this, you can look at the summary of what these points are: A, B, C, D, E, and F. A, initial pH of the acid, no base added. Point B is sort of before the half equivalence point. We don't really know. It doesn't really matter. It's just somewhere between 0 and the half equivalence point. Point C is at the half equivalence point. So at that half equivalence point, the concentration of the acid is the same as the concentration of the anion that's left over after the acid donates its proton, and therefore the pH is equal to the pKa. And in our case here, the value is 3.4. And if you look at point C, you can look at this graph and go, well, that's kind of like halfway between well, let's look at it a couple of ways. The volume of base that I've added is exactly halfway between no base added and the equivalence point of 50 milliliters. Well, that makes it the half equivalence point. So at that half equivalence point, half of 50 is 25. You go up, go on the x-axis at 25, you go up, you see point C, okay? Now, past the half equivalence point is point D, so the concentration of HA is starting to become less than A minus. pH is more than pKa, and at the equivalence point, that's where we switch from Ka to Kb. And the reason we do this is because now we have the conjugate base, which acts as the only base because it is the only base. And so now we can write that reaction expression, A minus plus water forms HA plus OH minus, and we can do our pH calculation. Really, we're doing a pOH calculation, and then we can subtract that from 14 to get pH. And then past the equivalence point, now I have excess OH minus. So I don't really need the conjugate base anymore because now I've got a strong base that's driving the rapid rise in pH deep up into the basic regime of pH. All right, that's it for our weak acid plus strong base experiment. The next thing we're going to tackle is the opposite, or the converse. We're going to tackle a strong acid and a weak base, and we'll see what happens when we do that experiment. And we'll see that really it's the same thing, only the curve is the mirror image of this. But we'll go through these calculations, so stay tuned.